Okay, good morning, good afternoon, good evening, good night, depending on when you're watching this video. In this illustration, we are going to be working through exercise number 1 from slide 32 of lecture set 5. So we're going to cover 2 topics in this illustration. Finding the area underneath any normal curve. So we are not working with strictly standard normal curves anymore. We are using a normal curve with any mean and any standard deviation, and we're going to find the area underneath those curves. Then what we're going to do is find values for a normal distribution that mark different percentiles or mark the point at which you will observe a particular area to the left or right of that point for any normal curve. In both cases, our strategy is essentially to work with the techniques that we have developed for standard normal curves and then use those in the context of these more general situations. Okay, so we'll start with an example, which is the first one. Okay, first off, our information is the carapace length of one species of tarantula is normally distributed with mu equals 18.14 millimeters and sigma equals 1.76 millimeters. All right, so in general, what we're being told here is that the variable of interest is carapace length. Okay, so this is what we're measuring. Okay. And this variable follows a normal distribution. Okay, so carapace length or you could say carapace length is normally distributed. Okay, so that means that we already can visualize the distribution of these lengths. So we know that this particular distribution okay, so this distribution is going to be a bell curve right? But this bell curve is going to be centered at 18.14. So that's the mean. And if we move one standard deviation in each direction, we move 1.76 millimeters. So for example, if we move one standard deviation from the mean in this direction, we're going to have 18.14 plus 1.76. And here we're going to have 18.4 minus 1.76. All right. And then from the empirical rule, we know that this area here is about 68% of the area underneath the curve. Okay, so this is a size of 0.68. All right, so that's just a bit of background. So just to understand what we're working with in the context of these problems. All right. So in the first problem, we're starting with a example of finding area underneath the curve. So we're going to be using the same curve that I had sketched out before, or we can use this same curve that I sketched out before to highlight the areas that we're going to be working with. All right, so for example, in part A, we are asked what proportion of this species have carapace lengths above 19 millimeters. All right, so what does this mean? Well, if we take our normal curve, okay, so we can erase these parts here, right? We just need the mean. So if we take a sketch of a normal curve, you can redraw the curve. You don't have to use the exact same one. Right now, what we're going to do is we're going to mark down roughly where 19 is. We don't have to be precise, but we know that the middle is 18.14. So the 19, let's say, is going to be right about here. Okay. Right, and what we want is this area here. So what we're looking for in this problem is the size of this area to the right of 19 millimeters. Okay. So this is not all that different from what we were talking about with standard normal curves. With standard normal curves, we would look at the same types of problems, except that we were always centered at 0 and we always had standard deviation 1. Now we can be centered at anything, for example, 18.14, and our standard deviation can be any number, for example, 1.76, but we still have the same style of problems. All right, so to solve this, all we're going to do is actually turn this into a standard normal problem. So we have, in terms of probability statements, the probability that x is greater than 19. Okay, so I'm letting x represent the carapace length. And that's pretty standard. Okay, we can technically use any letter that we want. X is usually what we use. And you don't have to define it necessarily. You can just go right to x. That's usually understood to be a normal value in the context of these problems. All right, so we want the probability x is greater than 19. So we're going to take our value, 19, and we're going to turn it into a z-score. Okay, so we have, so recall that z is equal to x minus mu over sigma. So z is equal to 19 minus 18.14 divided by 1.76. So z in this problem is equal to 0.49. Right? And we only need 2 decimal spots because the standard normal table only gives us 2 decimal spots of accuracy. So now we have a z-score that represents the value of x. So this problem becomes, what is the probability z is greater than 0.49? So what we've done here is we've transformed our question about area under the curve for this particular distribution into a z-score problem. So the probability that x is greater than 19 is the same thing as the probability z is greater than 0.49, where z is our standard normal random value. So what we do now is we go to our standard normal table. We look up 0.49. Okay, so here's z, here's 0.4, here's 0.09. So if we intersect those two values, we have 0.6879. Okay. Now this is the value, this is the probability that z is less than 0.49. We want the probability that z is greater than 0.49. So we just have to subtract this value from 1, and that gives us the answer. All right. Okay, so this thing is 1 minus the probability that z is less than 0.49. So this is 1 minus 0.6879. Okay, so that's 0.3121. Ah, come on. Okay, let's try. All right, whatever. All right. So there you have it. And again, in these style of problems, what we're actually doing is we're just transforming whatever the general problem is. So whenever we're working with any normal curve, once we know the population is normal, as long as we have the mean and the standard deviation, we can find area under the curve, or we can mark percentiles of that curve. And we do that simply by using our standard normal technique. So we turn the problem into a standard normal problem, or we start from standard normal and we work our way out to the general problem. So this is an example of finding area underneath a normal curve. And again, you can see that all we did here was transform it into a standard normal problem. So once we're comfortable working with the standard normal table, we can use that in any situation. Okay, let's look at another example. So part B says, what percentage of this species have carapace length between 17 and 18 millimeters? All right, so same idea, right? So let's take our standard normal curve from before. Okay, so this time we're interested in finding the probability that the species have a length between 17 and 18 millimeters. All right, so we have to mark down where we think those values are. Again, we don't have to be precise. These are just rough approximations. So let's say 17 is here, and let's say 18 is here. So we are looking for this area right here. Okay, so this is what we want. Okay, so here we have the probability 17 is less than X is less than 18. Okay, so whenever we're trying to find area in between two values, we know that this is found by taking the probability of the larger value and subtracting the probability of the smaller value. So the probability that that the value is between 17 and 18 is equal to the probability the value is less than 18 minus the probability the value is less than 17. Okay, so now all we have to do is convert each limit into a z-score. So we have z is x minus mu over sigma. So we have z is equal to 18 minus 18.14 over 1.76. This gives us negative 0.65. And we have z is equal to 17 minus 18.14 over 1.76. And this gives us negative 0.08. Okay. So now what we have, the probability negative 0.08 is less than x is less than negative 0, or sorry, yeah, is less than negative 0.65. Sorry, and this is a z. Okay, so now we've converted this into a z-score problem. So this thing becomes the probability z is less than negative 0.65 minus the probability that z is less than negative 0.08. Okay, so if we go to our standard normal table now, so we're working with two negative values. So we have negative 0.65. So here's negative 0.6. Here's 5. So that's 0.2578. And then we go back to our table, and now we're going to look up negative 0.08. So here's negative 0.0. This column represents the 0.8. Oh, sorry, I made a mistake. Mhm. Oh, I see what I did. Copied these wrong. There we go. This makes way more sense now. Okay. Okay. Sorry about that. All right. So, yes, this is. Thought that seemed a bit off. Okay, so now it makes sense. Okay, so we had 0.2578 for the first one. All right, and then we have 0.4681 for this value. There we go. All right, and then this is going to give us 0.2103. Okay, so the probability that a carapace length is between 17 and 18 millimeters is 0.2578. 0.2103. Sorry. Yikes. Right. C. All right, in part C, we have calculate and interpret the 90th percentile for carapace lengths. Okay, so whenever we see interpret, that means explain what the result means. All right, first off, what are we looking for here? So what we want to do in this question is we want to find the value of x that marks the 90th percentile of the curve. Okay, so we go here, we're just roughly labeling this, and what we're looking for is x 0.10. Okay, so this is what we want. All right, so we want this value. And this value is such that this side of the curve here is 0.9. Okay. Okay, so we want the 90th percentile. So that means that we want the value of x that puts 90% of the area under the curve to its left. So the reason, again, that this is marked x subscript 0.1 is because if we have 90% to the left or 0.9 to the left, then we must have size 0.1 to the right. And our subscript notation always gives us area to the right. Okay, so x subscript 0.1 means that there is 0.1 of the area to the right of the value such that the other 90% is to the left. And we want the 90th percentile, which means that we have 90% of the area to the left. Okay, so in order to solve this problem, we start with a standard normal value. So we start by saying find z subscript 0.1. So what we want to do here is find the z score that corresponds to the 90th percentile of the standard normal table. So we want to find z subscript 0.1. So there's two ways we can do this. The most direct way is we go to our standard normal table, okay, and we look up 0.9 inside the table. Okay. So we're scrolling through the table here, and then we have this value, 0.8997. Right, so this value here is the closest that we can get to 0.9. So this is the area underneath the standard normal curve. So this is effectively the 89.97th, 89.97th percentile of the standard normal, which is as close as we can get to the 90th percentile. So we come out to the axes and we have 1.28. So this is saying from the table that the 90th percentile of the standard normal table or the standard normal curve is 1.28. Okay. So Z subscript 0.1 is 1.28. Now, the other way you could do this is you could go to the normal table. You could look up 0.1 directly, which is right. The closest you're going to get to 0.1 is right here, 0.1003. Okay. And if you come out to the axes, you can see that you have, in this case, negative 1.28 again. But we have to if we look it up in the negative table, we have negative 1.28. But you have to remember that if the percentile or the area under the curve exceeds 0.5, then it has to be a positive value. So if we have more than 0.5 to the left, it has to be a positive value. Or if we have less than 0.5 to the right, it has to be a positive value. So you can look up 0.1 in the table directly, but you'll find the negative 1.28, and then you have to make the adjustment to the positive yourself by recognizing that if you're looking for the 90th percentile, this has to be a positive value because 50% of the area is on each side of 0, or because 0 is the median, which is the 50th percentile. Okay, so now what we do is we convert to x. So we've shown how this formula works before, but from the equation given above, so from z equals x minus mu over sigma, we can rearrange to show that x is equal to z sigma plus mu. And these steps are given up a few slides back. Okay, so that means that x 0.10 is equal to 1.28 times 1.76 plus 18.14, which is equal to 20.393. Okay. All right, so that's our 90th percentile. Okay, so this is the value that puts 90% of the area to the right. So now we were asked to interpret. So we can say 90% of this species. So 90% of this species of tarantula have carapace length below 20.393 millimeters. Okay. So we have found the value that marks the 90th percentile. So this is the value that splits the data into 90% on the lower half and 10% on the upper half. So we could also say 10% of this species of tarantula have carapace lengths above 20.393. That would also be reasonable in this situation. Okay, last problem here. Part D. What carapace length marks the upper 5% of this distribution? So this is actually the exact same style of problem as part C. It's just the language has changed. So now what we're saying is we want the length that marks the upper 5%. So we're being told directly in the problem that we want the value here such that this is a size 0.05. So when the question says what value marks the upper 5%, it's telling you the right tail area. So this value is directly x subscript 0.05. And now from this point, everything is exactly the same as it was in the previous problem. We start off by finding z 0.05. Okay, so if we have 0.05 to the right, that means that we must have 0.95 to the left. So if we look up directly 0.95 in our normal table, we'll see here that this is one of the special cases where the Z score is the average of two quantities. So we have 0.9495, 0.9505. Those values are equidistant from 0.95, which is what we want. So we're going to average 1.64 and 1.65, right? So this is a special case, and it only happens in this and one other situation that we end up with a 3-digit Z-score. Okay, so this value here is 1.64 plus 1.65 divided by 2 equals 1.645, right? So anytime you have the Z-score with 0.5 of the area to the right, it's going to be this 1.645. All right, and then we have X 0.05 is Z 0.05 times sigma plus mu. This is 1.645 times 1.716 plus 18.14. Sorry, this is just 1.76. All right, and that gives us 21.035. Okay, so that's our value. And I don't think we're asked to interpret, but just for completeness. So here what we could say is 5% of this species of tarantula have carapace length above 21.035 millimeters. And you could also say, and it wouldn't be incorrect to say it this way, 95% of this species of tarantula have carapace length below 21.035 millimeters. All right, so we have seen 2 examples of finding area underneath a normal curve that is not standard normal. So that's part A and part B. And in both cases, all we really had to do was take our problem and turn it into a standard normal problem. So we use the formula Z equals X minus mu over sigma to convert the limits of the values we are working with to Z scores, and then we found the areas corresponding to those Z scores. In the second 2 problems, part C and part D, we went in the opposite direction. So we were looking for percentiles of the normal curve we're working with. In this case, you start by finding the percentile of the standard normal curve, and then you use that value and convert back to the, you use the parameters of the normal curve that you're working with to convert that Z score back into the units of the problem. Okay, as always, if you have any questions, please let me know.